Hello everyone and welcome back to the Polaris School of Quantum. In today's episode of The Hidden Quantum Champion, we are going to look at a company called Menlo Systems, a company that is based in Germany, and we will learn a little bit more about what they're actually doing, which is related to light and the Nobel Prize even. And if this sounds interesting to you, then stay tuned for today's video, and we are hopping right into their website now. So here we are. It says Menlo Systems, leading in precision. It says Menlo Systems, headquartered in Mariensried near Munich, is a leading developer and supplier of cutting-edge instrumentation for high-precision metrology. Our Nobel Prize-winning frequency comp technology is internationally recognized as a benchmark for precision and reliability. With subsidiaries in the US, Japan, and China, and a global distribution network, Menlo Systems is closely connected to its customers from science and industry around the world. Our main product lines are optical frequency comps, ultra-stable microwave systems, solutions for time and frequency distribution, terahertz systems, femtoseconds lasers, ultra-stable lasers, and complete systems for quantum technology applications. In addition, we design and manufacture custom solutions for laser-based precision instruments. So you see it's a lot in the optical instrumentation and high precision instrumentation area, but there's also something related here to quantum technology applications, and I guess we will learn a little bit more about that in today's video, because that's what we want to look into. But before that, let's quickly continue scrolling down the starting page. So here it says precision tools for cutting edge applications. You see the different instruments or products that they are selling. So there's the optical frequency comp here, which is, let's say, at the core of their technology stack. There's ultra-stable lasers, quantum laser systems. So here it already starts to get interesting. Turnkey laser platforms for quantum optics and quantum 2.0 experiments. And there is more over here, like femtosecond and microwave lasers, distribution solutions, and so on and so forth. Detectors, whatever you need. Where precision meets possibility. And then down here you see the different technology branches that they are catering to. So Menlo, advanced laser and frequency comp technologies, enables breakthrough applications in fields spanning quantum science and technologies, metrology, spectroscopy, radar, quality control, and test and measurement in semiconductor industry. Discover how our solutions power innovation and deliver unparalleled accuracy across the scientific and commercial landscapes. And we will look, of course, into the quantum technologies in a second. Just scrolling all the way down here, where you can see that there's also the latest news and highlights in here. So there we actually see the frequency comp solution for the quantum 0.2 revolution. And we will check that one out in a second. But let's quickly hop into the quantum technology part over here. So how is this company actually related to quantum technology, and which role does it actually play in this whole quantum technology ecosystem? So quantum technologies are revolutionizing industries by leveraging the unparalleled precision and computational power of quantum mechanics. This is related to the quantum computers, right? And the quantum sensors. This makes them indispensable for tackling complex global challenges like quantum computing, ultra-precise sensing, and secure communication. So this is also quantum communication, of course, because that is like quantum key distribution and so on, right? You need lasers or light sources for this. Many of these applications require laser light, phase stabilized to optical frequency comps. And then quickly in the enabling technologies here. So behind every breakthrough lies a set of technologies that make it possible. These innovations tackle critical challenges and turn ambitious ideas into high-performance solutions for our customers. So sub-hertz ultra-low noise lasers. We maintain how we maintain coherence in quantum processors and quantum networks. Quantum systems require extremely narrow light width and phase stable lasers to maintain qubit coherence during long computations or complex gate operations in neutral atom or ion-based platforms, and preserve entanglement fidelity over long-distance fiber optics links in quantum key distribution networks. So here we see both of these cases, right? So there are, let's say, the particle-based quantum computing technologies like neutral atoms and also ions, and we've talked about these before. In the ions, you have microwave technology and optical wavelength, and then for the quantum key distribution, so in the optical range, so in the communication range, you're usually using telco wavelength, because then you can make use of the existing fiber infrastructure. And here it says, and of course, these are all, let's say, the points that are required, right? You have to have a long coherence because you are working over a certain period of time with these systems. You are doing your operations, so complex gate operations, which require multiple pulses, for example, shot at different atoms or ions, and therefore you need to have a certain amount of coherence, otherwise you cannot operate properly. And then, of course, and that's also something that we've seen looking at quantum communication companies, a benchmark is really the fidelity over long distance and also over long time. So these play a role in order to make sure that you have a reliable quantum key distribution and can actually make use of that in your application. So their solution is the ultra-stable lasers and compact optical references. We provide robust tools to support coherence across quantum systems, ultra-stable lasers with sub-hertz line width and ultra-low phase noise for reliable qubit control, compact optical reference cavities, so ORCs, with specialized coatings for broad atomic species compatibility, then custom ORS compact lasers, for example, the 1762 nanometers for high power narrow line width applications, and then telecom wavelength. I mentioned that also before. ORCs enable stable field deployable QKD anchors, no vacuum or maintenance required. Then there's this second rider here, which talks about spectral purity transfer, how we transfer sub-hertz stability across wavelength, locking all required lasers in a quantum setup to individual cavities quickly blows up complexity. Spectral purity must be reliably transferred to control lasers addressing various transitions. So transitions, I guess, referring to different optical transitions, so quantum transitions, quantum state transitions. The FC 1500 ULN plus frequency camp enables precise phase coherent frequency transfers cavity stability to any wavelength via the camp's teeth. CEP stabilization ensures absolute phase coherence, critical for Rydberg state excitation, so that's in the neutral atoms, right, and multi-photon quantum logic gates. Delivers fractional frequency stability with less than 5 times 10 to the minus 18 in 1 second, and ideal for dual species quantum control or systems requiring laser synchronization at multiple wavelengths. And that's again catering to the frequency count technique, right? Now, before we come to the third one, quick drinking break. Always make sure to have something to drink with you and stay hydrated. So we come to the integrated multi-laser control, how we manage multiple stable lasers for quantum systems. So quantum computers typically require many different laser frequencies for operations like qubit manipulation. That's what we talked about, right? The gates. But there's also cooling, trapping, state preparation, and ionization. So if you have an ion trap quantum computer, you first need to take the neutral atoms like rubidium or whatever you are intending to use, I don't know, and you need to ionize them. So you need to remove an electron. That you can do, for example, with a laser. Then you might want to do state preparation. So you want to get your particle into the ground state, your ion into the ground state from some excited state. So you have to make sure that you can trigger certain transitions such that it can actually decay, for example, from a very stable state it can be excited into another state which is less stable and then decay back into the ground state. So that's something which you can, for example, trigger with a laser at a specific wavelength. Then you can also use them for trapping, because lasers create electromagnetic fields. Ions have an electric charge, so with an electromagnetic field you can actually trap an electric charge, right? And then there's also cooling. I also mentioned that previously. There are techniques like, for example, Doppler cooling, which are very important when you want to create those ion trap computers, because you also here need to cool down your quantum system so that you can actually do operations down to the single qubit with it. So, going back to the text, this leads to increasingly complex, hard to scale optical setups. Again, because you have so many different laser frequencies, and again, that's catering to the frequency comp idea, right? So our solution is the FC1500 Quantum all-in-one solution. The FC1500 Quantum contains an ultra-stable reference laser, ORS, and a state-of-the-art frequency comp, which is the FC1500 ULN+, and the FC1500 ULN Nova, or Smart Comp, along with as many CV lasers as are required for your experiment. Menlo's patented Figure 9 mode locking technology allows transfer of the ORS spectral purity, narrow line width, and high stability to multiple laser sources, and enables down division of the RF, so radio frequency domain, without loss of phase coherence. This all-in-one system dramatically reduces system complexity while enhancing spectral purity across all lasers. Then there's some more information also here about the different products that were also mentioned before. So you here see, for example, the ORS. Here's the full system, the FC1500 Quantum. There's also some project highlight here. I guess that's one project that they've been involved in. I will actually not go into the details now for the time reasoning. Then there's also some quantum tuning for semiconductors mentioned here, and some fundamental information about the three different areas that we mentioned before, which was the quantum computing, sensing, and communication, as well as a contact here to the expert and business developer in the quantum market. Now let's hop back to the original page, because there was something else which I quickly needed to or wanted to look into with you, which is this Photonics Spectra Quantum Summit 2025 frequency comp solution of the Quantum 2.0 revolution. So there's this event coming up. I'm recording this mid of November 19th, and very quickly wanted to go through this talk notes here to see how close this is also entangled, right? And entanglement, of course, in the quantum sense. So the advent of the Quantum 2.0 revolution places new demands on photonic technologies, requiring unprecedented levels of stability, precision, and scalability. Optical frequency comps provide a unique solution to these challenges, offering phase-coherent links between optical and microwave domains, which again play, for example, in ion trap computing quite a role, high-resolution spectroscopy capabilities, and then timing precision at the femtosecond scale. This contribution highlights recent advances in the design and implementation of optical frequency comps, focusing on their critical role as an enabling technology for quantum communication, quantum sensing, and optical clocks. By providing phase-coherent optical references across broad spectral ranges, frequency comps facilitate precise qubit control, enable high-fidelity interconnections between separate quantum systems, and support synchronization for complex multi-qubit operations. These capabilities address fundamental challenges in developing large-scale distributed quantum information platforms and help realize scalable, modular, and versatile architectures in trapped ion and neutral atom computing. So really, it goes all the way down to, let's say, the fundamental technologies of these two platforms. So not this time not really on the hardware platforms like superconductors and spin qubits, but more on the neutral atoms and the ion trap. But there's another thing here, the optical clocks, which is very interesting and goes into the direction of quantum sensors. So using photons as optical, as time measurement instruments, so clocks, right? And I have this other page open here, which is also from Menlo Systems, and I quickly want to walk you through that one because I also find this a very interesting topic in the relation of what technology they offer. So it says advanced quantum clock for real-world applications. Optical atomic clocks serve as frequency standards that offer unprecedented precision in time measurements, making them the focus of research and technology development all over the globe. The accuracy can be as high as 1 second over the time span of 14 billion years, the age of the universe. By facilitating a transition in the hundreds of terahertz frequency regime, these devices outperform clocks based on transitions in the microwave frequency range by orders of magnitude. And this is like, think about your, quartz crystal electronic watch. This is very, very unprecise compared to these types of systems, right? However, the current state-of-the-art optical atomic clocks suffer from a large footprint that typically fills an entire optical laboratory. So that's why there's only a limited amount of facilities that can really, let's say, standardize time measurements with these atomic clocks, right? So the Acura aims to address this issue by developing a compact strontium-based lattice clock for in-field deployment with a performance rivaling that of lab-based clock. The development of compact and robust optical clocks is an important step towards their use in real-world applications and eventually space. And again, that is, of course, playing a role, one, when you want to think about interplanetary travel, but of course also thinking about GPS, where timing also plays a role. So, they would greatly improve the performance of technologies fundamental to telecommunication, geology, astronomy, and ultimately affect real-world applications and consumer devices. For instance, it would boost the accuracy of global navigation of satellite systems, so GNSS, and that's basically what I mentioned before, from the meter to the millimeter scale or even below, providing the necessary resolution for autonomous driving systems. While within the project, Menlo Systems is leading the design and engineering and subsequent integration of the Acura clock. So this is another example of, let's say, a quantum sensor, this time a time sensor. It is using quantum technology and it is using latest developments to miniaturize probably not miniaturize, but to make what is existent already much smaller so that it can be applied over a much broader range of different applications. So very interesting from my point of view, something that can already be contributing to, let's say, a lot of valuable, or catering to a lot of valuable cases, probably within the next couple of years. But of course, I don't know the timeline. I cannot tell anything about the precise details here. Okay, so with that, let's quickly check out the company side as well. So precision and photonics, together we shape a sustainable future, is what they are saying here, turning Nobel Prize winning science into technology. And a quick note on the frequency comp. It's also, I think, probably, it's more than 10 years ago, but I was actually in Garching in Munich, there's a research area in Munich called Garching Campus, I think, campus where there's a lot of research facilities, and actually I was there at one of the places, or at one of the labs where the frequency comp was probably developed, or where the Nobel Prize winners were actually working on that. So it was very interesting to see this area, to kind of feel the aura of this very special place where there's like researchers that won the Nobel Prize that have been working there. But yeah, maybe just as a side note. So Menlo Systems, headquartered in Martinsried near Munich, is a leading developer and supplier of cutting-edge instrumentation for high-precision metrology. Our Nobel Prize-winning frequency count technology is internationally recognized as a benchmark for precision and reliability. I think we've seen this part already. They have 200 plus employees. They were founded in 2001. So now it's 2025, so 24 years ago, turning 25. Here's the founding partners, and Theodor Hensch might be a name here in this context. Of course, the other ones as well. And then here there's some statement here. So leading in precision, our mission is to accelerate the advancement of optical technology for precision measurements and their applications from the tabletops of research laboratories to standard use in communication and high technology industries. Our aim is to serve our customers in pursuing their visions and ideas. Who we are, Menlo Systems was founded in 2001 by Professor Dr. Theodor W. Hensch, Roland Holzwald, and Michael May and Alex Kabel as a spin-off from the renowned Max Planck Institute for Quantum Optics, MPQ, in Garching near Munich. Organized in a GmbH, the company counts more than 200 employees, the majority having a university degree in physics or engineering, united by the passion of precision in photonics. With the two industrial partners, Hamamatsu and Thorlabs, together we shape light in a unique way. And that's also something that we can see here. So these are the two partners. And one of these two, I will not tell you which one, I've already featured in a previous episode of this Hidden Champion series. If you don't know which one, make sure to go to the channel and check out after this video of course, the playlist with all the Hidden Champion videos and check out which one it was. Then a quick statement here on the mission. So the invention of the optical frequency count technology, a revolutionary and simple technique for measuring the frequency of light, has called the biggest advance in precision electromagnetic measurements since people began to measure laser frequencies in the 70s. Our mission is to accelerate the advancement of optical technology for precision measurements and the applications from the tabletops of research laboratories to standard use in communication and high technology industries. Our aim is to serve our customers in pursuing their visions and ideas. Our hope is to create a place of highly skilled people in an open environment. Products and markets, I will not go through all of this. I think we've seen before that it applies throughout various different applications. And then there's also something here, Menlo Systems worldwide. I think that's also something that we've seen, that they have subsidiaries or offices in various different places. So here it says Menlo Systems headquarters is located in Martinsried near Munich. We operate our US subsidiary in Boulder, Colorado, where it conducts in-house production, development, sales, and comprehensive customer support to serve clients across the US and Canada. In China, we have Menlo Systems Quantum Laser Technology Co. Limited with its co-location with Thorlabs China in Shanghai. It allows us to give excellent technical support as well as excellent and in-time service to Chinese customers. In Japan, with Menlo Systems KK and the partnership with Hamamatsu, we have excellent support for Japanese customers. Our qualified engineers located at our subsidiaries guarantee excellent technical support as well as in-time service. For our customers, we offer webinars, and we've seen some of those before on the websites, frequency count seminars, technology seminars, as well as application seminars at our headquarters, as well as in selected places worldwide. And then here we have the technology partners and some research partners of theirs, as well as a quick note here on the Nobel Prize in 2005. So congratulations to our founding partner Ted Hensch, who was awarded with the Nobel Prize in 2005 for his contribution to the development of laser-based precision spectroscopy, including the optical frequency comp technique. The Nobel Prize awarded technology was the starting point of our company, Menlo Systems. Congratulations also to John L. Hall and Roy Glauber, who shared the Nobel Prize together with Ted Hensch. Hensch is director of the Max Planck Institute für Quantenoptik, quantum optics, and professor for experimental physics and laser spectroscopy at the Ludwig-Maximilians-Universität in Munich, Bavaria, Germany. And with that, I think we are already at the end of today's video. I hope you liked it. If so, please also give it a like and share it with a friend. If you don't want to miss out on the next episode, make sure to subscribe. And if you haven't seen all of the videos yet, also check out the playlist with all the other Hidden Champions videos. And with that, as always, make sure to stay hydrated and see you in the next one. Bye bye.